If you had to slide a small marble from point A to point B as fast as possible, what's the best path to take? A straight line seems the obvious answer. It's the shortest distance, so it should also be the fastest. But that's wrong. In fact, if you race someone who took a curved path, they'd beat you to the bottom every time. This isn't just a weird physics trick, it's a fundamental law of motion, one that baffled the greatest mathematicians for centuries. In 1696, Johann Bernoulli posed a challenge: find the path that gets an object from one point to another in the least time under gravity. It turned out, the answer wasn't a straight ramp or even a simple curve. The fastest path, the Brachistochrone Curve, was something much stranger. Something nature itself seems to favor in ways that go far beyond rolling objects. So why does this curve work? What does it have to do with roller coasters, space travel, and even quantum mechanics? And how did one of history's greatest minds solve it in a single night? Let's find out. The challenge: Johann Bernoulli's problem. In 1696, Johann Bernoulli posed a problem that would go down as one of the greatest mathematical challenges of all time. The question was simple. Given 2 points at different heights, what is the quickest path a bead would take under gravity if there were no friction? Not the shortest path, the fastest. Most people would instinctively say it's a straight line. After all, the shortest distance between 2 points is always a straight line. That's true in everyday life, but motion under gravity follows different rules. A straight path doesn't take advantage of acceleration properly. It starts too slow and doesn't build up enough speed early on. Bernoulli knew this. He wasn't asking a random question, he suspected that nature followed hidden principles of efficiency. He called the problem the Brachistochrone, from the Greek words brachistos, meaning shortest, and chronos, meaning time. He believed the answer would reveal something fundamental about how objects move, not just on Earth, but where gravity exists. So he issued a challenge. He sent his problem to the greatest mathematicians of his time, including Isaac Newton and Gottfried Leibniz, the co-founders of calculus. This wasn't just a friendly puzzle, it was a test of pure mathematical genius, a way for Bernoulli to see who was truly capable of understanding nature's hidden rules. And he didn't give them unlimited time. He set a deadline of 6 months. If they were as brilliant as their reputation suggested, they'd find the answer before then. If not, well, maybe they weren't as great as people thought. This was a bold move. Bernoulli was famous, but he wasn't Newton famous. Newton was the scientific figure of his era, a man who had revolutionized physics, invented calculus, and basically rewritten how people understood the universe. Bernoulli respected him, but this challenge was almost like poking a sleeping bear, and when Newton eventually got the problem, his response would become legendary. But before we get to that, let's talk about why this problem was so difficult. The key issue was that this wasn't just a geometry problem, it was a problem of optimization. You weren't just finding a shape, you were finding a path that minimized time. That's a much harder thing to calculate. Think about it like this. If you take a steep drop at the start, you'll pick up speed quickly, which is good. But if the path is too steep, you might not have enough horizontal motion to reach the goal fast enough. On the other hand, if you go too shallow, you won't build up enough speed in the first place. The perfect solution would need to balance both effects, picking up speed early while still maintaining efficient movement toward the destination. At the time, there was no easy way to solve this. Mathematicians didn't have modern tools like computers or software to test different curves. They had to rely on pure mathematical reasoning, and the tools they did have, basic calculus and geometry, weren't enough to crack the problem in an obvious way. But Bernoulli was confident the answer existed. He had a hunch that the curve wasn't something random, but something fundamental to nature, something deeply tied to the way objects move when left to themselves. He just needed someone smart enough to find it. And as it turned out, One man didn't even need 6 months. He took one look at the problem and solved it overnight. His name? Isaac Newton. The discovery: the shape of time-efficient motion. When Newton received Bernoulli's challenge, he didn't respond right away. In fact, he wasn't even supposed to be solving maths problems. By this point in his life, he was busy running the Royal Mint in London, dealing with England's economy and catching counterfeiters. But when he finally looked at the problem, something in him must have clicked. He couldn't resist the intellectual allure of the problem. The legend goes that he sat down, worked through the night, and had the answer by morning. No hesitation, no wasted time, just pure mathematical firepower. He didn't even bother sending a letter back with an explanation, just the correct answer. When Bernoulli saw it, he immediately recognized the style of reasoning and reportedly said, "I recognize the lion by his claw," acknowledging Newton's unmistakable mathematical prowess, even though the solution was unsigned. So, what was the answer? The fastest path between 2 points under gravity is not a straight line. It's a special kind of curve called a cycloid, the same shape traced by a point on the rim of a rolling wheel. If you've ever watched a bicycle wheel spinning and tracked a dot on the tire, you've seen a cycloid in action. But why is this curve so special? It all comes down to acceleration. When an object moves under gravity, it gains speed the longer it falls. The Brachistochrone curve takes advantage of this by starting with a steep drop. Right away it builds up speed much faster than a straight line. But then, instead of continuing to drop straight down, the curve flattens out, allowing the object to maintain that speed as it moves toward its destination. In contrast, a straight line path is inefficient. It doesn't let gravity do enough work early on, so the object moves too slowly at the start and never fully makes up for it. Meanwhile, a more extreme drop, something closer to a vertical freefall, would waste too much motion in the wrong direction, requiring extra time to correct its course. The Brachistochrone is the perfect balance. It gets fast quickly and then carries that speed efficiently to the finish line. This was a profound result. It wasn't just a mathematical trick, it was a fundamental insight into how motion works. The path that minimizes time isn't random, it follows a rule that nature itself seems to obey. The cycloid is the path gravity wants to take. To prove this wasn't just a theoretical result, Bernoulli and other mathematicians later built physical versions of the problem. Ramps shaped like different curves and raced objects down them. Every time the Brachistochrone curve won. Even more interestingly, it turns out this curve appears in places far beyond rolling objects. It shows up in light paths, space travel, and even quantum physics. Because at its core, it's not just about rolling marbles, it's about how nature optimizes motion. But before we get into that, we need to talk about something even deeper, the principle of least action. The idea that connects this curve to the fundamental laws of the universe. Why this curve matters. The principle of least action. At first glance, the Brachistochrone curve might seem like just a mathematical trick, a neat solution to a rolling bead problem. But it's much bigger than that. The reason this curve is so special is that it follows a deep rule about how nature operates, something called the principle of least action. What does that mean? Well, let's step back and ask a different question. When light travels from one point to another, does it always take the shortest path? You might think so, but that's not exactly true. If light moves through different materials, like air and water, it bends. It doesn't just go in a straight line, it follows a path that minimizes the total time it takes to get from point A to point B. This is known as Fermat's principle, and it's strikingly similar to the Brachistochrone problem. Fermat's principle, a fundamental concept in optics, states that light always follows the path that requires the least time. When light encounters a boundary between two media with different refractive indices, it refracts, adjusting its trajectory to maintain efficiency. Remarkably, this principle echoes the Brachistochrone problem. where a bead rolling under gravity does not take the straight line path, but instead follows a cycloid to reach its destination in the shortest time. Both phenomena reflect nature's inherent tendency toward optimization, not merely in distance, but in time and efficiency. In fact, the entire universe seems to favor paths that minimize something, whether it's time, energy, or some other physical quantity. The principle of least action is a way of saying that things don't just move randomly, they move in the most efficient way possible, according to the laws of physics. The path of the cycloid demonstrates nature's tendency to conserve energy while performing work. The bead uses gravity's potential energy in an optimal way to minimize the time taken, showing how nature can achieve an outcome with the least energy expenditure over time. Nature often selects paths or forms that are not necessarily the simplest geometrically, but are optimized for the dynamics involved. Similarly, engineers often mimic nature's solutions in design. The Brachistochrone curve can be seen in applications like roller coaster tracks, or even in the design of lenses in optics where light paths are optimized for efficiency. In chaotic systems, patterns like fractals and attractors emerge, revealing a deeper order within the complexity. This order is a direct consequence of the underlying optimization principle. For example, the fractal structure of coastlines or the branching patterns of trees can be seen as nature optimizing energy dissipation or resource distribution, consistent with least action. In every domain, nature reveals a preference for solutions that balance effort and outcome, showing us that efficiency is a fundamental principle woven into the fabric of reality. Newton's laws of motion can actually be rewritten using this principle. Instead of describing how forces push objects, you can describe motion by saying that objects follow the path that minimizes a certain quantity called action, a combination of energy and time. The Brachistochrone curve is an example of this action. It's the path that minimizes travel time under gravity. This idea wasn't just a clever way to solve a rolling bead problem. It became one of the foundations of modern physics. It's what led to the Lagrangian and Hamiltonian formulations of mechanics, which are now used in everything from classical physics to quantum mechanics. This principle appears in astronomy, engineering, computer science, and even economics. Any system that involves optimization, whether it's designing efficient transportation routes, predicting how planets move, or even training artificial intelligence, can be understood using variations of this principle. So when Bernoulli posed his challenge in 1696, he wasn't just asking for a solution to a math problem. He was unknowingly tapping into one of the deepest laws of nature, something that applies everywhere from the motion of planets to the weird behavior of quantum particles. But this raises another question. If nature is so good at optimizing motion, where else can we see this principle at work in the real world? The answer might just surprise you, because the Brachistochrone curve isn't just a mathematical curiosity, it shows up in some of the most unexpected places, from roller coasters to space travel. If you've ever been on a roller coaster, you've experienced the Brachistochrone curve without realizing it. The most thrilling rides don't just drop you straight down, they start with a steep descent, then gradually level out. That's because a straight drop isn't the fastest way to get through the course. By mimicking the Brachistochrone, roller coasters build up speed efficiently while still ensuring a smooth and fast ride. Engineers use this concept to design coasters that maximize acceleration early on, making the ride feel both faster and more exciting. When spacecraft navigate through space, they don't simply take a straight line path from point A to point B. Space travel isn't just about covering distance, it's about optimizing time and fuel. Instead of brute forcing their way forward, space agencies use gravity assists, carefully planned maneuvers that allow a spacecraft to slingshot around a planet, gaining speed with minimal energy expenditure. This approach mirrors the Brachistochrone curve, which shows that the fastest route isn't always the most direct. Similarly, during a rocket launch, the goal is to achieve escape velocity using the least amount of fuel. The initial ascent follows a steep trajectory to quickly gain speed while minimizing time spent in the descent part of the atmosphere. Much like how the Brachistochrone starts steep for rapid acceleration before transitioning into a more efficient path. Missions like Voyager and Cassini use this very principle, leveraging planetary gravity to accelerate efficiently. Just as a bead rolling along a Brachistochrone reaches the bottom faster than one on a straight incline, spacecraft achieve faster and more efficient journeys by following curved, energy-efficient trajectories rather than forcing their way through space. While real-world rocket paths don't perfectly trace a cycloid due to factors like atmospheric resistance, gravity shifts, and propulsion limitations, the underlying philosophy of the Brachistochrone, finding the most efficient path under given constraints, very much applies. It's not just physical objects that follow these optimized paths, so does information. When you load a web page, your data isn't traveling in a straight line from the server to your device. Instead, the internet finds the fastest route, considering factors like traffic congestion and server response times to minimize delays. Just like the Brachistochrone Curve reveals the fastest way for an object to travel under gravity, routing algorithms determine the most efficient way for data to move across the internet. If one route is congested, data takes an alternative path, much like a traveler avoiding a traffic jam. Latency, the time it takes for information to move from one point to another, is minimized in the same way nature seeks the quickest descent. Even server load plays a role, as data flows through less busy servers to reduce response times, just as physical systems naturally optimize movement to reduce resistance. The same mathematical principles that govern the Brachistochrone problem, seeking the most efficient path under given constraints, are at work in internet routing. Whether it's objects in motion, spacecraft navigating space, or data flowing through networks, nature and technology alike follow the logic of efficiency. This kind of optimization is critical in finance too. High-frequency trading firms use similar math to minimize the time it takes for their transactions to be executed, sometimes optimizing down to the level of microseconds. While the Brachistochrone directly applies to physical motion, its principle of optimization resonates with evolutionary biology. Evolution tends to favor energy-efficient solutions, whether it's the way blood vessels branch in the human body or the way animals move. When animals migrate, they don't always take the shortest path. They take the path that minimizes energy expenditure, which often resembles a Brachistochrone-like curve over long distances. Similarly, species adapt traits that optimize survival and efficiency, much like how the cycloid optimizes travel time under gravity. For example, the structure of bones or the shape of wings in birds are optimized for strength, weight, and aerodynamics. Even human decision-making follows optimization principles. When we solve problems or plan routes, our brains subconsciously look for the most efficient ways to do things. This is why when you're walking across a park, you might naturally take a curved path instead of a straight one, because it minimizes effort over the terrain. Similarly, biological systems use feedback loops to adjust behavior or structure for optimal performance. For instance, homeostasis in the human body ensures conditions like temperature, pH, or glucose levels are kept within narrow ranges, optimizing life processes. So, what started out as a simple problem, what's the fastest way for a marble to roll down, turns out to be a deep principle that shows up everywhere. The Brachistochrone curve isn't just about motion, it's about efficiency. It's a mathematical fingerprint that appears across physics, engineering, biology, and even human behavior. But perhaps the strangest place it shows up is in quantum physics, where the very fabric of reality seems to choose the most efficient paths. And that takes us to something even more mind-bending: how the Brachistochrone connects to the quantum world. At first glance, a rolling bead and a quantum particle don't seem to have much in common. One follows the predictable laws of classical mechanics, moving under the influence of gravity along a curved path. The other exists in a strange world of probability waves, superpositions, and uncertainty. But if there's one thing physics keeps teaching us, is that patterns in nature tend to repeat at different scales. The same principle that determines the fastest rolling path for a bead, the Brachistochrone, also plays a fundamental role in quantum mechanics. It all comes down to a simple but profound idea. Nature always seems to choose the most efficient path. In classical mechanics, if you throw a ball, its path is predictable. It follows a parabola, determined by Newton's laws. But in quantum mechanics, things get weird. According to Richard Feynman's path integral formulation, a quantum particle doesn't just take one path. It takes every possible path from point A to point B simultaneously. That means if you send an electron from one place to another, it theoretically explores every possible trajectory, including completely ridiculous ones like looping through space or bouncing off distant galaxies. But not all these paths contribute equally. The ones that interfere constructively, the ones that nature favors, are the paths that minimize a quantity called action. And what does that sound like? The Brachistochrone. Just like how the Brachistochrone curve is the mathematically optimal path for minimizing time under gravity, quantum particles tend to choose paths that minimize action. In other words, the very same mathematical principle that governs a bead rolling down a ramp also governs the fundamental laws of reality at the smallest scales. In quantum mechanics, there's something called the quantum Brachistochrone problem, which asks, what is the fastest possible way to transform a quantum state into another? Just like in classical physics, the fastest transition between two states isn't always the simplest or most direct. Quantum systems evolve over time according to the Schrödinger equation, and researchers have found that the principles behind the Brachistochrone curve can be applied to quantum computation, quantum gates, and even time evolution of particles. This has real-world implications. If you're designing a quantum computer, you want it to perform operations as quickly as possible, minimizing errors caused by environmental noise. Understanding the fastest possible transformations in quantum states is crucial for making quantum computing practical. And once again, the mathematics of the Brachistochrone is at play. Both classical and quantum systems exhibit a deep tendency toward efficiency, whether it's minimizing time, energy, or action, suggesting that nature itself is governed by an intrinsic drive toward optimal solutions. In the quantum world, systems evolve along paths that optimize certain constraints. This reveals a profound unity in the laws of physics, where the quest for efficiency transcends scale, connecting the macroscopic and microscopic realms. What does all this mean? It means the universe, at both large and small scales, doesn't waste time or energy. Whether it's a bead rolling down a ramp, light bending through glass, planets following curved orbits, or electrons jumping between quantum states, motion follows optimal paths. The fact that the same mathematical principle appears in such widely different areas of physics suggests that optimization is a fundamental role of reality itself. The Brachistochrone problem wasn't just a 17th century curiosity. It was an early glimpse into a deep, underlying principle that governs everything from classical mechanics to quantum theory. But there's still one more thing to consider. If the universe is built on efficiency and optimization, what does that mean for us? Is everything we experience shaped by invisible principles of least action? Why does the universe favor efficiency? Think about how rivers carve their paths. Water doesn't flow in a straight line. It finds the most efficient way downhill, often forming curved, optimized paths. The same goes for light bending through glass, the orbits of planets, and even the way human bodies optimize movement. Evolution itself is a process of optimization. Biological systems adapt to maximize survival with minimal wasted effort. But why? Why does nature always seem to find the best way to do things? One possible answer is that the laws of physics naturally select for efficiency. Objects don't move randomly. They follow well-defined rules that minimize waste. In a way, the principle of least action and the Brachistochrone Curve reveal something profound. The universe isn't just a chaotic mess of motion, it's an organized system that follows deeply embedded mathematical principles. Nature's drive toward optimization isn't the result of conscious thought or decision-making. Rather, systems that operate efficiently are the ones that persist, replicate, and maintain stability within the constraints of the universe. Over time, this leads to a natural selection of processes, behaviors, and structures that are not just functional, but inherently optimized for their environment. Efficiency isn't an accident. It's woven into the fabric of reality itself. This principle doesn't just apply to physics, it applies to human behavior too. Even in art and music, efficiency plays a role. The best designs, melodies, and structures tend to balance complexity with simplicity, an optimized form of expression that feels right. The Brachistochrone Curve is just one example of a deeper pattern in nature. We see it everywhere. Light follows the fastest possible path, Fermat's principle. Objects move to minimize action, Lagrangian mechanics. Quantum particles take all paths, but the ones that win follow optimized principles, Feynman's path integrals. Evolution favors energy-efficient survival strategies. So what started as a simple physics problem in the 1600s turned out to be a fundamental rule of existence. The universe optimizes. It finds the best path, and whether we're aware of it or not, we're part of that process too. But now, let's bring it back to where we started. If you were to slide from point A to point B, what's the fastest way down? The answer isn't a straight line. It's something far more elegant, something that reveals the hidden mathematics shaping our world. And once you see it, you start to notice it everywhere.